reactions, they happen everywhere, in the air that we breathe, in the water that we drink, even in the rocks that are in the mountains, and everywhere. There are some reactions that are quite obvious to us because they are fast. For example, when we're in the kitchen, we turn on the stove, the fire is burning blue and orange. That is a fast reaction. Burning is an example of a fast reaction. And there are reactions that are even faster than that, even more explosive than that. For example, burning of hydrogen gas. In the lab, when we test for hydrogen gas, in the small test tube, we hear a pop. Now imagine an intense amount of hydrogen, concentrated hydrogen, and then you ignite it. You're going to get, instead of a pop, you're going to get a boom, all right? And then there are reactions that are a little slower than that. For example, beer makers, wine makers, all right? When they take yeast or other form of bacteria and they combine it with a sugar sauce, such as apple, rice, grapes, and they ferment it for 2 weeks. What you get out of it instead is carbon dioxide, which is the little frothy layer on top of beer, right? And alcohol, right? So that is a process that's a little slower. There's even reactions that are even slower than that. For example, if you had a bicycle that has been crashed and you scrape the paint off the bicycle frame. Now, leave it out there in the open for a few months or years, you pick up your bike and you see brown rust on it. Rusting is another example of a chemical reaction that's a little slower. And then there are chemical reactions that are not so obvious to us. For example, the weathering of the rocks. You've probably seen movies of the Grand Canyon, or gone to the Grand Canyon itself, and you see like far beyond the horizon, you see plains, but tall mountain ranges shooting way up, right? And the mountain ranges are like that, like really just vertically high, and you're down there somewhere, all right? And it does not make sense. It just looks so unnatural. Why? Because the hard rocks will not be prone to chemical weathering, right? But the softer rocks, like maybe limestone, will be more susceptible to undergo weathering, which is a type of chemical reaction that is a little slower, and these reactions can take centuries and millions of years, all right? So, but for us humans, why is understanding these rates of reaction important to us? It's important for two reasons: money, cha-ching, and safety. You gotta wear your safety goggles. Okay? Money. Well, if we can improve the rate of reaction, if we can improve the efficiency of the rate of reaction, we can make the reaction go faster. We can save money or make more money, or a combination of the both. All right? And that's just basically what underpins all kinds of industrial process. It's just to make money. But there's also another reason that's quite important. For example, you want to improve safety for your workforce. So if you own a mining area, and you are extracting minerals in the mine, and you have really skilled employees that are already doing a good job down in the mine. You want to monitor gas levels and also flammable dust levels and toxic gas levels, because you basically don't want a freak accident. Let's just say that. You don't want a freak accident to happen where someone or something gets sparked. There's a spark source that just occurred, and suddenly kaboom! The whole mining shaft is like gone. All right. right? Or if you are like flour mill, where you are milling all this rice or potatoes or wheat into your flour powder that you use to bake cakes and make bread and stuff like that. Now, you want to monitor that the dust level is low, and also to prevent any spark source, because once the spark is ignited and the spark catches onto a dust particle or flour particle, and then a chain reaction will happen and you get a huge explosions. All right? So those are the two important things on why understanding the rates of reactions are important. First is to make money, save money. And secondly is so that you won't have your employees blowing up to bits and pieces every week or so. All right? That's safety. Now, to understand how we control the rate of reaction, thereby making more money and improving safety, is that we need to understand the collision theory of particles, the collision theory on how successful reactions do occur. Now, here I have a little diagram where I start with a reactant. These particles, reactant particles, are moving in all random directions. Some are moving fast, some are moving slow, some have high kinetic energy, some have low kinetic energy. And they'll bump and collide and move in all random directions, hitting the container wall or hitting each other. Now, upon lots and lots of collisions, some of them will result in a successful collision where bonds are broken and new bonds are formed to make new products. That successful collision requires that the reaction overcome the minimum activation energy required. All right, so when particles are colliding, it may overcome that minimum activation energy to make new products. So when reaction starts happening, a lot of collision will occur, and then after a while, the reactants gets used up, and you finally end up with products. Okay? So that is the collision theory. First, you have to understand that not all reactions are successful. Secondly, you have to understand that there's a wide range of kinetic energy that's happening here, here, and here. In fact, some reactions, products may bump each other really hard with the reactants over itself or whatever, and you may overcome that reverse activation energy to form the reactants again. Whoa, that's like mind-blowing stuff. But let's not think that way, but think of reactions as just moving forward. But in real life, it's very dynamic. It's moving forward and backwards, and lots of random stuff that our human brain just can't really comprehend. So let's just think of it as a forward momentum, right? Okay, reactants, you form the products, after you overcome the minimum activation energy, and then once all the products are formed, very little reactants are available to have successful collisions, all right? So now that you get a basic generalization of collision theory, let us try to understand in the next few lessons how to improve successful reactions. Thereby, we can first reduce the particle size, thereby increasing the surface area, or we can make changes to the temperature and pressure of it, all right, to the reaction vessel. We can introduce catalysts such as transition metals or enzymes in order to lower the activation energy in order for more fruitful, successful collisions to occur. We can increase the concentration of the reactants, thereby having more reactants available for collisions. We can use light as a way to induce bonds to break or overcome the minimum activation energy required. So there we go.